Today I'd like to talk about some advanced techniques for solving more complicated DC resistor circuits. And the first technique we're going to talk about is called superposition. So you've probably heard superposition before in physics, and that is when we're talking about things like electric fields or magnetic fields. If we have two sources of electric field, the total field from those two sources is just the vector sum of the individual fields from the two. So they just add together. That's what superposition means. In this context, it means basically the same thing. The idea is if we have more than one source, meaning a voltage source or a current source in a circuit, the current through any particular element is just the sum of the current through it that is caused by one source plus the current through it, that is caused by the other source. So our way of stating that, the current in each element of our DC resistor network is the sum of the currents from each source. And I will say here that direction matters. So if we get, one source gives, so here's our resistor, it's connected to some other stuff. One of our sources gives a current this way, I1, and the other source gives a current this way, I2. The net current is going to be like I1 minus I2. Or if we get that from the two sources, they're in the same direction, then we're just going to add those two currents together and get some bigger number. It is certainly possible that these two cancel out exactly, and in that case, you have some balance in your circuit that means that component doesn't have any current flowing at all. That can happen. So the rule to apply when we're doing this is, what do we do with the other sources? If we're looking at the effect of just one source, how do we treat the other sources in our network? So if there are other voltage sources, we want that voltage source to not be doing anything. So we want it to have a voltage of 0, which means that is the same as a short circuit, which means we replace our source just with a wire. So something that looks like this, we replace with something that just looks like this, just a wire. If we have current sources, if we want to eliminate their effect, we would set their current to 0 amps, which means that we actually want an open circuit. Which means we just leave a gap or a hole in the circuit. So if we have something that looks like this, that turns into something that looks like this. It is just disconnected in our circuit. So these are the rules. Let's do an example just in case this doesn't make sense. While I'm erasing, I will say this is only useful if we have multiple sources. Because for each one source, we still have to solve the rest of the circuit with some other technique. So let's do just a full example of this. So let's say we have a circuit that looks like this. This is about the simplest circuit this is going to be useful for. I chose to do it with two voltage sources. I thought about having one of them be a current source instead of a voltage source, but I don't know, I picked this. So this voltage source is 18 volts, this one is 8 volts, and we have three resistors, a 3 kilo ohm, a 2 kilo ohm, and a 6 kilo ohm. I'm going to keep this color-coded so we can tell our two individual solutions apart. So first, let's look at what happens just from the 8-volt source. So our circuit is going to, maybe I'll do it over here. So our circuit's going to look like this. 8-volt source. And my 18-volt source I'm replacing with 0 volts, that is just a wire. So you'll notice now that my 3K and my 6K resistors are in parallel, right? These ends are connected together and these ends are also connected together. So I can replace them with a single resistor that has a value of 6 times 3 over 6 plus 3. So that's 18 divided by 9, which is 2 kiloohms. So I have two kilo ohm resistors. I have my 8 volts. So that is going to give me, looking at this as a voltage divider, I have 2 equal resistances. So this point is going to be half of my 8 volts. That is 4 volts. So now going back to this picture, that point is 4 volts. And now we can figure out all of the currents from that. So my 2K resistor has a voltage difference of 4 volts, and I equals V over R, so that's 4 volts divided by 2 kiloohms gives me 2 milliamps of current. My 3 kilo ohm and my 6 kilo ohm resistor also have 4 volts across them, right? If we're calling this 0 volts down here, this has a difference of 4 volts. This has a difference of 4 volts. So that means my current through the 3 kilo ohm is 4/3 of a milliamp. We'll keep this exact for now. And through my 6 kilo ohm, it is 4/6, which is 2/3 of a milliamp. So I'm going to draw the solutions from this one in red on the board. And my units are milliamps. I'm just going to leave my units off of this. Okay. While I'm erasing this, note that we can check Kirchhoff's current law at that junction. And does 2 milliamps equal 4/3 plus 2/3? Well, 4/3 plus 2/3 equals 6/3, which is 2. So that works. That's good. Okay, now let's do our 18 volt supply quickly. It will be exactly the same technique. So now my 2K and my 6K are in parallel, and I've replaced my 8 volt source with just a wire. So 2 kilo ohms in parallel with 6 kilo ohms is 2 times 6, which is 12, over 2 plus 6, that is 8. So 12/8 is 1.5. So I end up with an equivalent circuit that looks like this: 18 volts, 3 kilo ohms, and 1.5 kilo ohms. Okay, so like before, we would like to know what the voltage is at that point between them. Using the voltage divider equation, this voltage is going to be 18 volts times whatever fraction this is of the total resistance. So that's 1.5 over 3 plus 1.5 is 4.5. So 1.5 over 4.5 is 1/3. So this is 18 over 3, which equals 6. So this point is at a voltage of 6 volts. And this point is equivalent to this point on our picture. And now we can figure out what the currents are, just like how we did before. So 6 volts across our 2 kilo ohm resistor gives us 3 milliamps to the right. 6 volts in our 6 kilo ohm resistor gives us 1 milliamp down. And here we have 18 minus 6 is 12. So we have 12 volts across our 3 kilo ohm resistor, which is going to give us 4 milliamps to the right. And note 4 equals 3 plus 1. So, okay, Kirchhoff's current law still works for that. So now our total, well, let's put these currents on the board. And this will give us our final answer. So superposition says we just have to add these two solutions together to give us the total currents in these components. So if I redraw my circuit, We have, so through the 3K resistor, we have 4 milliamps to the right and 4/3 milliamps to the left. So this is going to be 4 minus 4/3, which I can't do in my head, but I already wrote down. It is equal to 8/3. Oh yeah, because 4 is 12/3. So 12/3 minus 4/3 gives us 8/3. Okay, so we have 8/3 of a milliamp going to the right. Here we have 1 milliamp down and 2/3 of a milliamp down. So those are in the same direction. So we get 1 plus 2/3, which is 5/3. And finally, here we have 3 to the right and 2 to the left, which gives us a net current of 1 milliamp to the right. We can do one check, of course. 8/3 in to this junction is split into 5/3 and 3/3, which is 1. So that that checks out. Kirchhoff's current law holds. Let's just check a voltage loop law at some point on here, just to make sure to make sure we haven't done anything wrong. We might as well check if we can. So let's use the voltage law on a loop that looks like this. So starting here and going around this loop like that. So going from here to here, we're going opposite the direction of the current. So we must be increasing our voltage. So we are increasing our voltage by delta V equals I times R. So that's 5/3 of a milliamp times 6 kiloohms. Sorry, I'm not going to write equals yet. We'll do the actual math later. So that's I times R for this component. Then continuing our path around the circuit, going from here to here, we're going in the same direction as this 1 milliamp of current. So that's going to be a decrease in voltage of I times R. So that's 1 times 2 kiloohms. And then finally, going from here to here, we are going from the positive side to the negative side. So we are decreasing our potential by 8 volts. And then we end up back where we started. We're connected by a wire. So this is the whole loop around the circuit. So 5/3 times 6 is equal to 10, right? 5 times 6 is 30. So I have 10 minus 1 times 2 is 2, minus 8. And indeed, that does equal 0, just as it should from Kirchhoff's voltage law.